Alright, Avogadro and Avogadro's law. This is the last of the simple gas laws. This particular gas law relates the number of moles of a gas and the volume of that gas. So it is actually going to be the same relationship that we saw with Charles's law, just now with number of moles instead of the temperature. And so we're going to have a very similar looking equation here. We have V1 over N1 is equal to V2 over N2. Again, we're holding everything else constant, so the pressure and the temperature have to stay the same. We can't have those changing. The only two things that can be changing are the volume and the number of moles. One thing that's interesting here is that when we're talking about the number of moles, we don't actually care what the gas is. All we care about is how much of it there is. We don't care if it's nitrogen or oxygen or CO2 or sulfur hexafluoride. We don't care. All we care about is how many moles are there, how much of it is present. And if we plot this, what we'll see is that no matter what the gas is, it's always going to end up intercepting at 0, 0 down here, which should make sense. Because if we have 0 numbers of moles of gas, then we would have no volume. And so it should always intercept at 0, and then it is a linear relationship for the relationship between the volume and the number of moles. Again, because it is directly proportional, just like the temperature and the volume. As one of them goes up, the other one also goes up. And you can think of it again like a balloon and blowing into a balloon. If you have a balloon and you blow a little bit of gas into there, it expands. The volume increases. If you take the same balloon and you blow some more gas in there, you increase the number of moles. What happens to the balloon? It gets bigger. So it makes sense that it's directly proportional. You put twice as much gas in, you get twice the volume. Alright, so we're going to do some practice problems here with these simple gas laws, and I would highly encourage you to look at the next 3 slides here. Pause the video now and try to answer these questions on your own. When you've tried to work them out yourself, come back and see how you did. So go ahead and pause the video now. Alright, hopefully you have attempted the questions. We're going to go ahead and work through this one. This says that, as discussed in the opening section of this chapter, you inhale by increasing your lung volume. A woman has an initial lung volume of 2.75 liters, which is filled with air at an atmospheric pressure of 1.02 atmospheres. If she increases her lung volume to 3.25 without inhaling any additional air, which I don't think is actually technically physically possible, but we're going to pretend like it is, what is the pressure in her lungs? So we are trying to find P2. What is the pressure of the air in her lungs after doing this thing that she did? So I'm going to identify, first of all, what equation do I want to use? Well, the only thing that's changing is the pressure and the volume. So I'm going to be using Boyle's law. So the pressure times the volume is equal to a second pressure times the volume. I'm trying to find this, and hopefully I'm given everything else. And if I check here, I'm told the initial lung volume and pressure, and I'm told the final volume. So what I'm going to do is I'm actually going to go ahead and just do some math here, some algebra, to get P2 by itself, which is what I'm trying to find. So this tells me that P2 is equal to P1 times V1 over V2. And if I just go ahead and input what I know, Let's see here. I'm told that I started at 1.02 atmospheres and a volume of 2.75 liters, and that she ended with 3.25 liters. So if you notice here, my liters cancel out. So if I do that math, 1.02 times 2.75 divided by 3.25, I get 0.863 atmospheres is the pressure in her lungs if she was able to expand her lungs while keeping her mouth shut. Which again, I'm not entirely sure that's actually physically possible. Let's look at the next example here. A sample of gas has a volume of 2.8 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees C, its volume decreases to 2.57 liters. What is the initial temperature in Kelvin and degrees C? Okay. One thing I have not mentioned yet that I do need to mention at this point, which if you've already worked through this problem, don't be mad at me that I didn't mention it yet, but anytime you're working with temperature and gases, you always have to use Kelvin. Celsius is not going to work, and we can see that by actually writing this out. So if you remember, Charles's law is V1 over T1 is equal to V2 over T2. And if we just plug in what we know, V1, we're told, is 2.8 liters. T1 is what we're trying to find. It's the unknown initial temperature. V2, we're told, is 2.57 liters. And then we're told that the initial temperature is 0 degrees C. Now, the math people watching the video will automatically look at that and say, oh no, divide by 0. Not good, not good, not good. Anytime we're working with gases like this, we need to have Kelvin here instead of Celsius. So I'm going to go ahead and do some algebra to this first, actually. So again, this is just not good. There, we're going to ignore that for now. If I flip this, so if I multiply both sides by T2 over V2, I will get T2 times V1 over V2 times T1 is equal to 1. But I don't want T1 by itself down or over here. I want it over here by itself. And so I'm going to go ahead and multiply both sides by T1. And so that will give me T2 times V1 over V2 is equal to T1, which is what I'm looking for. And so if I go ahead and do plug in the math here, T2 is not 0 degrees C, that's going to be 273 Kelvin. Because remember, to convert to Kelvin, you just add 273. Since we're at 0, it's just 273. V1 was 2.8 liters. And V2 was 2.57 liters. So if I do that math, 273 times 2.8 divided by 2.57, T1 is 297.43 Kelvin. last example problem here. A male athlete in a kinesthesiology research study has a lung volume of 6.15 liters during a deep inhalation. That's a lot of gas. He's having 3.2 liters in his chest. At this volume, his lungs contain 0.254 moles of air. During exhalation, his lung volume decreases to 2.55 liters. How many moles of gas did the athlete exhale? Assume constant temperature and pressure. Alright, so since we're dealing with number of moles and volume, we're going to be looking at Avogadro's law. Nothing else is changing, so we can use Avogadro's law. What are we trying to find here? Well, if we look here, we're actually trying to find how many moles of gas did the athlete exhale. If you're not careful, it can kind of seem like we're trying to find N2. And that's not actually what we're trying to find. Because N2 is not the number of moles of gas that were exhaled. N2 is the number of moles of gas that are left after exhaling. So what we're actually trying to find is the difference between N1 and N2. Now we do have to find N2 in order to get that, but N2 is not going to be our final answer. So we're going to do algebra similar to in the last question. Essentially take everything on this side and flip it and put it over here, and then multiply everything by N2, and that will give us N2 is equal to V2 times N1 over V1. And so if we plug in what we know, let's see, V2 is 2.55 liters, N1 is 0.254 moles, and V1 is 6.15 liters. So my liters here cancel. If I solve for N2, I get 0.105 moles. Now, but again, this is not what I'm looking for. This is the number of moles of gas that are still in his lungs after he's exhaled. I'm looking for the amount of gas that was exhaled, and so that will be 0.105 minus the initial amount, 0.254. So he exhaled 0.14, let's just round that to 9. And I know I did kind of do that backwards there, so technically give me negative 0.149, which just kind of depending on the convention, because he did lose that number of moles. So the fact that it says he's exhaling kind of takes care of the fact that it's negative. It's essentially just the absolute value of the difference is what we're getting there. That's the number of moles that were exhaled. All right, I think we'll call it good there for this video. And in the next video, we will talk about the ideal gas law.